Okay, so let us start the class. I'm sharing my screen. Okay, so okay, this is so this is MPE 405 and QFT. This course is QFT, but path integral approach. Everybody can see the screen?
Yes, sir.
Yeah. Okay, good. So I'll teach all three classes according to this tentative timetable. That means almost 30 lecture according to our syllabus is prepared that 3 months with 3 lectures is 36 lectures. So around that, like many lectures will provide. Today, if it is of course in the revised timetable, if something changed, then I will do accordingly. Okay, so this quantum field theory, you have already learned little bit. So this first I'll introduce what you have learned, and then I'll tell you what I'm going to do in this course. So quantum field theory is basically quantum mechanics for fields. Fields, you know, anything which is function of space and time is called field. Anything which is, but it is a continuous variable. X can change continuously, time can change continuously. So quantum mechanics, 3 courses you have learned, and all 3 courses are with the particles. Quantum mechanics for particles. So now if you have the, instead of particles, if you have the fields, then and you have quantum description, then it is quantum field theory, right? Exactly same way you have learned that when you have a particle thing, you have done Coulomb's law, you have studied electrostatic kind of thing. But when you consider as a field, then you study Maxwell equations. So basically quantum mechanics, quantum theory, concept of quantum theory you have, now will apply to the fields. And motivation, what is the motivation? I'll come to all these books, etc. I'll just let me review what you have done. So motivation, that 3 motivation I wrote this. Relativistic quantum mechanics cannot explain when particle number of particle changes. Because relativistic quantum mechanics is valid when you have a microscopic system, particle moves with a velocity comparable to light velocity. Okay, but that relativistic quantum mechanics, which is supposed to be ideal, but cannot explain if the number of particles, in one state you have 10 particles, another state you have 7 particles, the relativistic quantum mechanics can tell how there will be transition from this to that. So you need to go to continuous variables. So discrete variables cannot describe that. Second motivation was the causality. This is very important. I explained in last class also, quantum field theory. Causality means there should be some cause and then effect will come. And this is not only true in physics, this is true in your life, whole life. Everywhere, daily life, everywhere causality. First cause, then effect. It cannot happen that effect will come first, then will cause. You may understand the cause later, but cause has to come first. For example, I push somebody and he fell down. I किसी को धक्का लगाया तो गिर गया. So that means that pushing is the cause. So that should be occurring first. Then falling down is the effect which will come later. So this is the sense of causality, and this causality violates in quantum mechanics. So causality effect that I explained last last semester also, that suppose some particle is created here, and you are measuring the probability of finding the particle, say in 5 into 10 to the power 5 kilometer away from it after 1 second of this creation. So light cannot travel 5 into 10 to the power 5 kilometer in 1 second. So light signal cannot travel there. But if you want to measure by using your quantum mechanics, you can find some non-zero probability. That means if you consider, so light cannot, or no signal can travel, go to that point, still you find that probability is non-zero. So that is the violation of causality, and it can be shown in relativistic quantum mechanics. It can be shown in non-relativistic quantum mechanics. This last year I discussed this. Those who want to learn it more, you can ask me or you can study. I can refer you where to study all this. So causality violates in quantum mechanics, and it is a big question mark how to explain. People says, okay, for a probabilistic theory, maybe causality is not that so important, or there are many bypass way of doing things, but causality, quantum mechanics has problem with causality. Third is that which is you all know, relativistic quantum mechanics has problem of negative energy solution, which is not acceptable. But Dirac, through his whole theory, is explained how negative energy can be explained, kind of thing. But all these are explaining by hand. It is not the kind of thing, natural solution. Okay, so all these three motivates you that we relativistic quantum mechanics is not adequate. You need to go to quantum field theory. Okay, and quantum field theory, where it is necessary, quantum mechanics is necessary in all branches of physics. Quantum field theory, quantum mechanics is for all branches of physics. So if you want to do anything in physics, then you need to know quantum mechanics very well. And QFT is considered to be the most difficult subject at the MSc level. Of course, in the physics, most understanding, it's a bit mathematical, it is abstract, and it is also difficult to understand this concept. So quantum field theory also, you need all branches, particularly I'll say that all theoretical branches of physics in it. You need in particle physics, you need in string theory, cosmology, astrophysics, you need this atomic physics, nuclear physics, you need this in condensed matter physics, both theory and experimentalist. If they want to explain theory, they also need the concept of quantum field theory. To performing the experiment, to set up the experiment, they may not need quantum field theory concept, but if they want to predict their experimental outcome properly, anything you want to explain, you need quantum field theory concept. In spectroscopy, in biophysics, everywhere you need quantum field theory. It is a quantum mechanics, but for fields. You will be surprised to know that these people in our time who used to do high energy physics, they learned quantum field theory very well. And the people who are other branches of physics not pay much attention to learning quantum field theory. Now, condensed matter theory or condensed matter physics become popular later. High energy physics is bit kind of saturated, that people think, And then for example, quantum mechanics, it is almost saturated subject. Similarly, quantum field theory, so people shifted towards condensed matter physics. And high energy people, those who knew quantum field theory, they shifted and they do remarkably well in condensed matter, and they actually captured the condensed matter group by the high energy physics people because they knew field theory. So field theory is very important, and it naturally provides the multi-particle, that the motivation that cannot particle number is changing. Why particle number will change? Because you know E equal to mc square, right? E equal to mc square, that means if you have a very high energy, it can create particles, or two particles can collide and can give rise to energy. Pair creation, pair annihilation, you are familiar. So when you are talking about microscopic system with moving very high velocity, there is a possibility of pair creation and annihilation. So that way particle number will change. But in last class in quantum field theory, if you have followed my lectures, classes, then I showed for scalar field theory how we can have the Fock space with particle number changing. So particle number changing situation can be dealt with this quantum field theory. So the most important thing is that QFT is the only field, only subject which can explain the spin statistics theorem. This you are familiar, right? There are, if in nature we find there are particles with 0 spin, half spin, 1 spin, etc. And they are classified in two ways. Those 0 and integer spin are called bosons, and half integer spin, particularly half 3/2, they are called fermions. So bosons satisfy Bose-Einstein statistics, certain kind of statistics, and electrons and other fermions, they satisfy Fermi-Dirac statistics. But why? How? Who said that they will satisfy these statistics? Where is the proof? And this proof can be done only in quantum field theory, and also with the advanced level of quantum field theory. Even we are not going to prove the spin statistics theorem in whatever field theory, elementary field theory we will learn in this course. So it can handle multi-particle situation, it can prove spin statistics theorem, it can give a solution to the causality problem. If you remember my last year classes, microscopic causality I discussed in the case of scalar field theory with the light cone and etc. That you have to remember. If you don't remember, you can revisit that class again. And provides the correct platform to any theoretical understanding of physics. Any level of theoretical understanding, deeper level of theoretical understanding of physics provides. Particularly those who are interested in particle physics or scattering cross sections, decay width, etc. calculation, field theory will be extremely useful. That I am going to show in this course. This course will mainly focus on Feynman approach, Feynman diagrams, Feynman calculation, and I'll teach at least one process that, for example, Rutherford scattering, electron muon Rutherford scattering, and we'll prove that formula which Rutherford often 1 over sine to the power 4 theta by 2 formula will prove from the quantum field theory. This calculation everybody will understand. And in the in this nuclear particle physics specialized student, they have the pion decay, muon decay, Newton decay, etc. Those only you can understand if you follow this quantum mechanics, quantum field theory lectures. That is why I said few of the nuclear physics students, there is overlap. So if you don't study quantum field theory, then it will be difficult, little bit difficult to understand those things. But this year I will not be teaching weak interaction paper. Earlier year I used to teach weak interaction also, but then Professor Malik will teach this year. Okay, so now quantum field theory you have learned, and so far what you have learned, let me summarize that. So first, you know how to deal with continuous system. So you know that Lagrangian density. That means how to go from discrete finite degrees of freedom, finite to infinite degrees of freedom. So you have a certain number of discrete system. From there, how you can go to a continuous system, and then instead of Lagrangian, you get a Lagrangian density, and then you know Euler Lagrangian equation to find equation of motion. And this you have done, and I am assuming that you know this with 4-vector notation. Anybody has any doubts, please clear those doubts. 4-vector notation will be using, and will be assuming that you are now master of 4-vector notation. So if you you know the Lagrangian density for scalar field, charge scalar field, electromagnetic field, Dirac field, and you know how to find the Kg equation, how to find Dirac equation, how to find Maxwell equation, etc. So this expertise is assumed that you all know that how to describe a scalar, charge scalar, electromagnetic, and Dirac fields free. So that is most important. So free, there is no interaction. The important difference of this course will be, we'll consider interaction in this course. So this first point is clear to everybody. Everybody knows this. Second point is the quantization. Quantization of fields that I have taught you. Some of them, some in the group P2 group, I taught quantization fields. Other group also, they learned from the other teachers that quantization of fields. So this, what is the meaning of quantization? I'll tell you. This is also called second quantization. So this, so what are the steps here? That steps are identify dynamical variables, dynamical field variables. That means fields and its momentum conjugate. Then make them upgrade as operators. So field operators, momentum operators in Hilbert space. Okay. Third point, you that put the quantization condition. So put commutation sometimes anti-commutation for Dirac fields particularly. So this step is actually the main point in the quantization, relation to quantize. Sometimes student cannot answer that what is the quantization in quantum mechanics. When you put them x px, commutator is IH cut, that moment you are quantizing theory. So all these are basically your, if you follow the postulate of quantum mechanics, first you identify the variables, dynamical variables, make them operators in a Hilbert space, first postulate. Second postulate will be that putting this, they satisfy certain commutation relation, or many people put this postulate in different ways. So the moment you put this, then, and you can find that what is the quantized field, for example pi, and this is field and momentum, and then you have learned that that these fields which has continuous variable of space time, function of continuous variable space time, is realize as collection of infinitely many infinite number of simple harmonic oscillator. So this is the big realization, and you have done this. When you calculate the first you decompose. When let me remind you, fourth point, when you write your field in terms of creation annihilation operator, you may remember the Fourier decomposition minus p det and a dagger p. This I am writing for real scalar field. dq p by root over etc 1 over 2 pi etc. Okay, so this the creation and annihilation operators, and this is infinitely many summed. Every creation operators is function of p, and p are infinitely many, minus infinity to plus infinity. So infinitely many harmonic oscillators are there. Similarly also in the pi also. And if you when you find the Hamiltonian, in case of one harmonic oscillator Hamiltonian in quantum mechanics, it is a dagger a plus half. Here you will find a integration over AP dagger and AP. So infinitely many creation annihilation operators, and there's some in field theory. So this is for simple harmonic oscillator, and in the scalar field you will find that P times EP by 2, and then a dagger P a P plus half delta 0. This you remember this formula. So this means that infinitely. So my point is that realization of any field theory as a collection of infinitely harmonic oscillator, this you have done. Okay. Now this is the step 2. Now third step is that to calculate the Hamiltonian. So you know Lagrangian density. From there you can calculate the Hamiltonian, again in terms of the simple harmonic oscillators, in terms of, and then you construct the state Fock space, whole Fock space, that number state, particle with quanta 1, particle with quanta 2, etc etc. So whole Fock space is constructed. Okay, so all state constructs the Fock space description, calculate the state. So this will give you the states. And also another thing which you have learned, which is not directly relevant, but you have the symmetries. Noether's theorem. What is that idea? Idea is that whenever you have certain symmetry in the theory, there will be a conserved quantity, and conserved quantities are helpful for studying the dynamics. If something is constant of motion, it is very helpful to study the dynamics, right? So this we have learned the Noether's theorem and conserved current, particularly translation, space-time translation, x mu prime going to x mu plus epsilon mu, space-time translation, and T mu nu was the conserved quantity energy momentum tensor that we found. And another thing is the gauge transformation. Gauge transformation leads to the conservation of charge. Conservation of charge. That also we discuss in the context of charge scalar field, the charge operator, how to calculate. So these symmetries and corresponding. So this much you have learned. And one important thing you were supposed to learn, but you have not learned, I also didn't teach because of lack of time in this P2 group also, that I'll mention, is the propagator. I'll tell you details about the propagator. But before that, let me know in this, I have just summarized that whole quantum field theory you have learned in last semester. Forget about mathematical details, concept wise. Does you recall that? But do you recall that these things? And do you have any problem in understanding any of this? First, let me conceptually. Mathematicals always can be very easy to find. Even I can provide notes if certain calculation is needed. You can do. propagator, I'll tell you the importance of these propagators, and because my first thing is to calculate the propagators. Um, but before that, let me know what I said. Summarize this one to any Lagrangian is given, you can find equation of motion. Lagrangian density also you can construct for these four fields. Okay. Then quantization. Quantization means dynamical variables are operators, and then you put the commutation relation. Then you find that the solution of the field and its momenta which satisfy those commutation relation. That will give you the realization of collection of infinitely many harmonic oscillator modes. So fields are realized through harmonic oscillator modes. Okay. Okay. Good. And then you calculate the Hamiltonian, and you find the Fock space, then symmetries. So these are the things you have learned. Now let me know if you have any doubts, difficulties, or some part which you have not learned, particularly the P1 group student. P2 group student, I know what I taught in the class, but so that you should let me know if you want to understand this. Okay, now what is the plan? Okay, or propagator, I'll come. Propagator you have not learned, but we're supposed to learn. Maybe in today's, towards the end of the class, I'll start propagator calculation, and it will be absolutely clear to you. Propagator is there in classical mechanics, propagator is there in quantum mechanics, propagator is there in quantum field theory. But unfortunate part of our teaching is that first time you are probably heard of this name. You should have heard in your undergraduate courses the propagator. But I'll tell you. Before that, let us plan of this course. Let us plan this course. This much field theory you have learned. So what else we are going to learn? First thing is that all this field theory were free. There was no interaction. So it was a free field theory. Now you are going to learn is the interacting. Interacting, let us write QFT. So you have seen this. The quantization we discussed, this quantization is called canonical quantization. Because we put the commutation relation between the canonical variables. So this quantization is called canonical quantization. But there is another quantization which unfortunately so far you have not done, but it should have been done in your quantum mechanics course. That is called path integral quantization. Most of the modern or good institutes in abroad, in the quantum mechanics, the advanced quantum mechanics course, this is there. And you can see in the quantum mechanics book by R. Shankar, there is 2 chapters on path integral quantum mechanics. Here we did canonical quantization. Now we are going to learn path integral quantization. So in this course, what is the difference? First will free theory, canonical quantization will be now interacting theory, and path integral quantization. Okay, so this is the main difference. This path integral quantization in our BHU syllabus in MPE 305, it is there. You are supposed to learn there, but I'm sure it was not taught in that course. When I used to take part in MPE 305, I used to teach path integral quantization, Berry phase, and other things. But Professor Malik only focus on general theory of relativity part and some other part. But that syllabus is big. I think it is not possible to teach all the topics in detail, but should have been taught. At least path integral quantum mechanics is not the difficult concept, easy concept. See, R. Shankar book has 2 chapters on that. Those who are interested, you can start reading R. Shankar. So in the interacting, we'll focus mainly on 2 theory. One is the scalar theory. That theory is called lambda 5-4. This 4 scalar field interact to the self interaction. So this is lambda 5-4 theory and quantum electrodynamics. So these 2 interacting theory will focus, and main teaching of this course will be the Feynman approach, Feynman diagrams, and Feynman rules to calculate different quantities like d sigma, d omega, there's decay width, lifetime of particle, and many other. But in Lamb's shift you can calculate. You can calculate anomalous magnetic moment of electron. All these things, quantities in field theory, you can calculate using Feynman diagrams and Feynman rules. So my course will be will focus mainly on Feynman approach. See, when you consider interacting theory, interaction cannot be dealt analytically. One has to do perturbative method. You know perturbation method. So perturbation method in field theory is giving a huge calculation, very long expression, long calculation. And Feynman is the person who made all these in very simple and in a diagrammatic way. He developed all this approach himself, and those are known as Feynman diagrams, Feynman rules. So he simplified that perturbation method for a alternative calculation, alternative way of calculation for d sigma, d omega, and many other calculations. Any physical quantity you need to calculate, you can do by Feynman diagram. So in this course, if you attend all the lectures, you will be learning to good amount of Feynman diagrams, how to draw Feynman diagrams, how to use Feynman rules to calculate these quantum field theoretic things. This you will learn very well in this course. Particularly those who are in particle physics, they cannot do pion decay, muon decay. This is a 1/3 part of your weak interaction 402B paper. 402B paper, pion decay, muon decay. Without Feynman diagrams, Feynman rules, you cannot calculate this. So if you don't learn Feynman diagrams, Feynman rules, you will not able to understand this. You can calculate things, but you will without learning. Then some part of the course, if time permits, will concentrate only 2 important and very advanced topic, is called renormalization. And renormalization group equation. Of course, I'll teach, but depending on how much time and how much you are getting understanding in this course. See, this is an elective course, so my pressure will not be there to finish the syllabus. Elective course will not have a pressure to finish the syllabus, but it is important to learn. So depending on your learning, I'll go to, of course I'll teach, but how details I'll teach this, depending on that how much you are learning the Feynman diagrams and other topics. So finishing syllabus is not a pressure, but we'll learn things in your space. If you want go slowly, we'll go learn slowly. If you want fast, we'll cover your syllabus. Okay, standard model of particle physics that got several Nobel Prize, and there is no single prediction which is wrong so far. Of course, it cannot explain certain things. Still now, there are beyond standard model physics is basically a quantum field theory model. So it's based on fully on quantum field theory. So if you want to learn standard model, you have to know quantum field theory very well. So standard model is the direction for those who want to do experimental theoretical particle physics direction. Okay, so this is that, and as usual, we'll have, I said, approximately 36 to 40 lectures we'll have, depending on how many holidays, where your exam, or where your last teaching day. So this kind of thing. So number of classes depends on that. We'll have tutorial class. So every 4 5 every 2 weeks there will be one tutorial class. So every after 5 lectures, the sixth lecture will be the tutorial class. So I can clear your doubts in these 4 lectures. I can discuss some problem set. So the tutorial class will be there. So every 2 weeks there will be a tutorial class at least. If you demand more, we can have more. 3 to 4 assignment set I'll give you. Depending on that, how much you interest, your interest, you will solve those problems. If you are very much interested in field theory, you solve all. But for your sessional grading, you have to submit only few problems. So I'll not create pressure on you for that. And one more additional thing that uh, that if you feel, if the student feel like, I generally give some additional lecture for your net and get preparation. So generally before these exams, I take 1 or 2 lectures to discuss typical problems in, particularly in quantum mechanics, classical mechanics, statistical mechanics, mathematical physics, etc. These are my subject areas. So this, so if students are interested, I can give say 2 lectures before net, 2 lecture before your gate exam, how to approach in the exam, how what are the important problems. See, I'll tell you, in quantum mechanics there is one principle in quantum mechanics, and every exam you will get question from that principle. If you understand that principle well, you will able to solve that problem. So this is the additional features of this my lecture. So this is all about plan. So do you have any question? Otherwise we'll go to the, so how much time we have? 20 minutes. Okay, so let me take a 1 minute break. If you have any question, please tell me. I hope you are listening now.
Yes, sir.
Hello. Yeah,
Yes, sir.
okay. Uh, Nowadays student just log in and then disappear also. And my, I'll suggest that people to come, if you are interested in my class, please join the class in time, just 1 2 minutes within the class, because once we start teaching, then if you join late, it is disturbance to the class. So I'll not allow you to join if you are late by 5 minutes, but I request you to join in 1 or 2 minutes within. After 5 minutes, you will not be allowed, but I'm requesting you to join within 1 or 2 minutes of sharing the. I'll share your link. Probably the same link will be using every day. So please keep this link safe, and the same link will be using. So I don't have to create a meeting link every time. Just joining. Okay, so now let me start with propagator. This is something which very important concept, and I used to teach in quantum mechanics 1 course when I used to teach this course alone. But the other section people, teachers told me not to teach propagator because they cannot cover that. So I didn't teach propagators. Also, we didn't have much time this year because your exam was earlier and we didn't have many lectures. So propagator, I'll spend at least one full lecture on propagator such that you can understand this. So propagator, let us see. This is an English word. So let us see the English meaning. What is the propagator? Probably you have heard this word propaganda, right? Propaganda word you must have heard. Uh, some propaganda or so propagator means in English. If you look at the dictionary, a person who spread or promotes some idea, The person who spread some idea or promotes some idea is called propagator. He propagates things. So this is English meaning is clear. Little bit technical meaning in the English dictionary is that a covered, typically heated container filled with soil or composite used for germinating or raising seedling. So from seed, if you want to make the plant, so to make it the grow faster, you covered some area, then maintain some temperature, putting soil or composite and then seeds, then it will the germination and the raising of seedling will be faster. So that is also called propagator. This is English dictionary. I'm just copying from some dictionary. So propagator is something which propagates. Where we discuss free theory, probably propagator was not important. Quantum mechanics, you have to calculate amplitude. So quantum mechanics, all you have to do calculation of amplitude or probability. So propagator is basically in field theory you will see it is basically gives you the amplitude. Propagator gives you the amplitude. Okay, so this is but field theory will come. So English word, one who spread or promotes some ideas called propagator, propaganda, you know, right? Also technical, little bit technical English meaning I told you. Now in quantum mechanics, let us see quantum mechanics. You are already familiar with propagator. So when you write your wave function at some later time t2 in terms of your wave function at some initial time t1, that you have, everybody has done, no? T2 greater than t1. T1 is earlier time and t2 is later time, and this is some operator u t2 t1, and this operator e to the power minus I h cut h t2 minus t1, I think, kind of thing. This is time evolution uh, operator. So I knew the wave function at some earlier time. How I calculate how it propagate to a new time t2 is given by this operator. So this is propagator. So this is a propagator. All you knew this, but not familiar with this name. Okay, so propagator is nothing new. That is why it can be introduced in even classical mechanics. Let me tell you in classical mechanics what is the propagator. So in classical mechanics, let us consider with the example. Suppose I have a mass spring system. Everybody has solved this problem. Who has come to a MSc level has solved this problem, I believe. There are 3 spring, 2 mass. Let us assume all these mass are same. All the spring has same spring constant. Okay, say rest length is 0. So you can write your differential equation. Everybody has written this x2 and x1 dot double dot and x2. So this is the variable of first mass. This is the variable of second mass. Then you have written this differential equation, coupled differential equation. So that coupled differential equation can be written in terms of a matrix time x1 x2. Coupled means it will be x2 also will be related to x1 and x2 also will be related to x2. Similarly, x1 will be related to x1 and x2. So I can write a matrix equation. This is nothing but a 2 cross 2 matrix. Okay, so now you find the solution. This coupled differential equation, you can find normal modes and then finding solution, and you can find your x1t and x2t at any time in terms of your x1 at 0 time and x2 at 0 time. When there is no oscillation, when they are at rest, this in terms of that, or t equal to 0 their position, that I can write. Again I can have a matrix 2 cross 2 matrix. Let us denote that as omega tilde. So what I had in the right hand side, I had the position variables of this mass spring system, first mass and second mass, at 0 time they were like this, and at any arbitrary time t1 t, I can find x1 and x2 through a matrix this. So this matrix is propagated. So this is a propagator, and it propagates and relate its 0 time with the finite time. This is a propagator. So this, I suggest those who are good student, suggest find this omega tilde, this solve this problem and find the propagator. That omega tilde you should find. It's half an hour job. If you have done this, you are, the differential equation is available with, try to find a solution and then you write this matrix and omega. So this is, find this omega tilde. This is kind of homework if you are interested. If you are not interested, even if I give 1,000 homeworks, you will the copy to get your sessional marks, but you will not learn. So I will not force you to learn anything. Okay. So now if you have any question, so now you have somebody ask you what is a propagator, you can answer. So let me tell you how to, or what is the importance of propagator in now in quantum field theory, particularly in real scalar field theory. I'll teach you how one can calculate the propagator. Now, I already told you this quantum field theory is bit mathematical. His big calculations, those are not very difficult, but lengthy calculations and bit abstract. Physics concepts are less, but mathematics are more in this course. That is why students don't like, I think. But those who have taken this course, they for the sake of their interest, sometimes I'll not do the mathematics. I'll those who are interested, they will ask me, and then I can provide as a notes those mathematics. Because anyway, it will, again, exam will be online kind of thing, and again we cannot ask those derivations in the exam. So no point of putting lot of time to do the derivation in the class. I'll give you the some derivation which is required, mathematical derivation, and you follow it. If you cannot follow, you just bring your question to me, I'll explain. Okay, so this year what I have taken this strategy to suppress certain mathematical derivation which will be supplied to you as a supplementary material. Okay, so now let us discuss the propagator in field theory. Let us start with the real scalar field. And real scalar field, you all know that it satisfies the Klein-Gordon equation, right? You should remember this. Real scalar field Lagrangian density, just to remind you, del mu phi minus m square by 2 phi square. So this del plus m square phi equal to 0 if there is for no source. If there is a source, then this equation, this right hand side will be replaced by the source. So in presence of source, this is the Klein-Gordon equation. So now let me remove those. So this, in the presence of source, this is your Klein-Gordon equation. Now try to find a solution, because propagate means it has to propagate. So we need to find a solution for this in presence of source. So how you find the solution where this source is present? You have found solution when there is no source, that free theory. Now when you consider interacting theory, then there will be think you are familiar with Green's function method. If you are not, I'll tell you enough in this few minutes that will understand the meaning of uh, uh, the Green's function. Okay. So Green's function is the solution of this equation. Green's function in the differential equation also is there. So differential Green's function is solution for unit source. So if Jx is replaced by a unit source means delta potential kind of thing. This is called unit source. Only in that x prime it has the source, other nowhere else. So the unit source for continuous system is like this. So when this j is replaced by this, the solution phi is known the Green's function. But it is related to delta function. So then we Green's function for this suppose is g of x minus x prime. So and for mathematical convenience, I'll write mathematical convenience. I write. So this delta operation is with respect to x. So let me write x m square phi x. No, not phi. Now Green's function. Now I'll write Green's function. G x minus x prime will be delta 4 x minus x prime by definition. But for mathematical convenience, we'll use a minus sign, nothing else. If you take plus sign also, but we'll prefer to write a minus sign. So this is called Green's function. Green's function is the solution of the inhomogeneous differential equation for unit source. It is a continuous system, so unit source is a delta function. For mathematical convenience, we have taken minus sign. You can have taken plus sign also. So what is the advantage of that? Once I know the Green's function, this Green's function, once I know it, then I can immediately find a solution of this equation, which is an inhomogeneous equation. We don't know J, but I can find a solution. Immediately I'll write the solution. The solution will be phi 0 of x minus. So if I take plus, then this will become as plus minus d4 x prime g of x minus x prime j of x prime. So this will be the solution of this equation. You can verify immediately. Where is phi 0? Phi 0 is solution for the free equation. That means delta x plus m square phi 0 x is 0. This is for free solution. So the inhomogeneous equation has a solution free part, then minus, which can be calculated using the Green's function. And this Green's function connect between x and x prime. So it can connect the, this is the solution. And this, if you look at this equation, Green's function equation, it connects between x and x prime. So this is nothing but the Green's propagator. So this is your propagator. So Green's functions are nothing but the propagators. So they are same. In some book, you'll find that sometimes they write Green's functions, sometimes they write propagators. So in field theoretic knowledge, but first let us verify this is a solution. So we put delta x plus m square. Just operate this, operate from both sides. So left hand side it will be phi x. This is my left hand side. Right hand side will write right hand side will be delta x plus m square times first term will be phi 0, which is 0. Now second term will be minus d4x. This is an x operator, so it will go inside the integration. Integration is x prime. So this box operation m square will act on the Green's function, and this is function of x prime, right? Second term. Now this we already know. This by definition of Green's function is minus delta 4. So this minus plus will be d4 x prime. Then it will be delta 4 x minus x prime j of x prime, and this is a delta function integration. This is d4, this is 4 delta function, so this is j of x. So this is your right hand side. So left hand side equal to right hand side. So this, so you understand that this is a solution of this inhomogeneous equation, and this is the whole idea of Green's function. I use the Green's function. What is Green's function? Is a solution of inhomogeneous equation, differential equation for unit source. And if I know the Green's function, I can find the solution of the inhomogeneous equation with arbitrary source. That's all. So simple physics is related to the Green's function. Now in our purpose, we need to calculate the Green's function in momentum space. Right? So how you do? If I know something in coordinate space, how I do that? I can go to the how I calculate in the momentum space. So let us write that is your GP, Green's function in momentum space, by Fourier transformation. You all are familiar. So let me write. I'll stop in 2 minutes. I have a meeting at 12 also. So Green's function at x prime will be d4p 2 pi to the power 4, and then e to the power minus I p dot x minus x prime and gp. This is nothing but a 4-dimensional Fourier. Okay, so maybe I'll stop here. It is exactly 12. So this is the from here. If you have any question, please go through whatever I told you in terms of only I taught you only the Green's function and nothing else today. But you go through it. If you have any doubts, you just bring it to me in the next class. So next class, I'll tell you, I'm expecting the new timetable by Monday, but let us see. If it is not there, Tuesday we have the class in the old timetable, so we'll take the class on Tuesday. If it is on Monday or some other day sometime, then accordingly we'll see. So maybe I'll stop the class today here. Any question?
No, sir.
Okay, so please go through it, and we'll discuss. So let me end the class to first. No, I should.